Welcome back to DeepRob for discussion 5. Today's discussion will be, I think, like the slide content is pretty short. It's just sort of going over the remaining project topics, which I didn't have time for last week. And then what I'm planning to do is sort of like we can have it more as like an office hour. So I want to kind of go around for those of you who are here in person, or if you stick around online, and we can maybe do it over the chat. And I just want to like give feedback on maybe what you're thinking about for projects, or if you've started to read some of the papers and want to talk a little bit about going through them, or if there's things that are confusing. I think discussion is a good time to kind of do that, especially because like generally I think like to be honest, like the students who come to discussion are usually like very, very motivated and excited about the content, which I love personally, because I'm very excited about this content too. So I think it's a good time for us to kind of like, go over the material. So before I start, I don't have any administrative updates other than just to mention that that paper selection survey is due tonight. So it's like a formal quiz within the grading scheme. So just a reminder to fill that out if you haven't done so. So this time could also be a good time for you to do that. But I guess before I just go over briefly the other topics, which we didn't cover last week, are there any administrative questions that I can answer in terms of projects or grading or office hours? You could do either way. So the question was for the paper selection quiz, should you like if you want to propose partners that you'll work with on your team, should you like strategically try to make sure that all of the partners on the same team pick the same topics? We'll do our best to make sure that everybody's matched with the partners that they want to work with, assuming that there's sort of agreement. Like we would like to see that like you would want to work with each other on the quiz. So we're going to do our best to like respect those requests. I can't say what we can like guarantee every partner, just because we do need to make sure that we kind of have some coverage over these other like all the topics. So I don't know what the distribution looks like in terms of what people want to work on or like review and present. So if you're thinking about it to that level, it's probably overthinking it. Like we'll do our best to match everybody up. Question. Okay, yeah, interesting. So the question was, if you change your mind about what your preferred paper is after submitting the quiz, is there going to be an option to switch papers? I will handle that, I guess, on a case-by-case basis. So if you feel the need to do that, like as a group, or if you're working as an individual, I'd say like let us know as soon as possible, because we did pick out these papers to some extent based on, so within each area, what we've tried to do is pick out papers that are both prominent, but also give a sense of what the history has been, at least recent history for these areas. So if you decide like you don't want to do a paper, then we'll just have to find another paper to sort of fill a hole potentially. So just let us know as soon as possible if you do decide like, oh, this paper is, for some reason, I really don't want to present on this paper. Just let the core staff know as soon as possible. Yeah. Good questions. One more maybe? Yeah. That's a really good question. So the question for those online was like within the final project overall set of deliverables, one of them is that extending an existing paper's results. And like, what does that mean? That seems very open-ended and very vague. And that is the intention, actually, to be honest, because that is like to give a sense of what research in this area is like when you submit a paper, you have to like that paper should have a set of contributions for the rest of the field. And what those contributions are is part of doing the research, like figuring out how to structure what a contribution will be before you've done the work is part of like what goes into research and planning out what work you're going to carry forward, like what work you're going to carry out. So I can't say because of that like open-endedness and that uncertainty that goes with research, I can't say you have to hit like this benchmark and this benchmark, because for everybody's project, it's going to be slightly different, like what the topic area is and what it might mean to even extend an idea. So to give some examples of what you could potentially do for like an extension, maybe you could take an existing code base and apply it to a new data set. Like, so maybe you could take it like one model that was made for you know, for grasp pose detection at the category level, and try and evaluate it on a data set of like maybe like example images of objects that from the same data set, but like in like low light conditions, or or try to apply a model that was trained on RGB data now with depth data. So those kind of like changes to like an input data type would be an example of like an extension. Another case might be, you might want to like take like a vision model and a language model and like put them together. So maybe like combining two existing models would be like one case of an extension. So it'll sort of depend on the topics that you want to pick. That's actually why I kind of want to start going around, like spending some of the time in discussion, kind of going around and talking with everyone, so that I can give more feedback on what you're thinking and just try to help with the kind of project development and some of these ideas. Yeah. Great. Okay. Any other administrative questions I can clarify? Yeah, good. Yeah, so the question was, so for like the seminar style discussions, so starting like roughly from week 8 on, are those lectures going to essentially just be like groups will present the paper and then we'll just move on to the next group, or will there be time for discussion? We're going to try to encourage discussion. So what we're planning to do, so we're going to spend, so this is our first time doing this course. So we're also trying to like figure it out too, like what makes the most sense and what's the most beneficial for the students. The plan is, so like next discussion, we're going to do a topic on how to review a paper. And then after that, we'll give a discussion section on how to like present a paper, like what things should go into a presentation. And so that should hopefully clarify some of those questions. And then on the topic though of what these seminar styles lectures will look like, what we're planning to do is roughly like every group will have sort of 10 minutes of structured content. So essentially like 10 slides is a good kind of benchmark for 10 minutes. And that would go over like the background that the paper presents, what's the problem they're trying to address, what are the techniques, what are the results, and then towards the end, like what does the paper describe as a conclusion, which usually would incorporate like the main takeaways, future work, questions that aren't solved. And hopefully that conclusion sort of slide that you'll have will prompt questions from the audience, or the other slides for that matter. So then we'll leave like maybe 5 to 10 more minutes for discussion amongst the full class. That's the goal. Thanks. Okay, so yeah, so getting into, so I'll just briefly, this might just take, roughly maybe 10 minutes, 15 minutes, something like that, to briefly kind of go over these remaining set of, I think it was like 4 more topic areas that we didn't have time for last semester or last week. And then like I was saying, we'll use the rest of the time for sort of like an extended office hours. So last time we left off, the final topic that we looked at was data sets. And we were sort of pointing out this importance of having access to data sets for our deep learning models, and also the expense that comes with collecting and human annotations for our data sets. So an interesting idea that has been picking up steam in some of the deep learning communities is this sub area called self-supervised learning. And at a high level, the goal of self-supervised learning models is generally to reduce the need for human annotated data. So instead of having human annotators label maybe every single segmentation of like, let's say like ImageNet, instead what you might want to do is try and define some automatic labeling process that can be used during training for your task. So a few examples, so these are from like the core list of papers. So this first one on the upper left, this was an example actually of, this is actually like tactile perception. So what they were doing was trying to have a self-supervised model that would encode RGB information together with proprioceptive, so like the joint states on a robotic arm, together with force and torque sensor readings. So the goal was, what they wanted to do was encode those 3 sources of sensor input together into some learned like latent space. So some learned feature vector would come out from this learned model. And then that learned feature vector would be used downstream in like a reinforcement learning network for actually like trying to like do tactile manipulation. So try to like put pegs into holes, or like move objects on a table. But one of the real challenges with actually applying reinforcement learning is that, especially with these large networks, which when you're taking image data as input, it's going to be a pretty large network. is you need a lot of simulation runs to actually have like a good model. So the part of the idea with this approach was if we could use self-supervised learning to maybe learn this encoder, then that might reduce how many simulation runs we need with a downstream reinforcement learning model if this encoding portion was frozen in the second stage. So what they try and do is self-supervise this encoding model by taking by basically using like deterministic like kind of calculable summarizations of these 3 input data types, and they'll try to sort of like learn to predict from these inputs the automatic labels. And so the automatic labels in this case was optical flow from the RGB information. And so optical flow is like a deterministic calculation that if you have a sequence of images, you don't need a human to annotate optical flow. You can just directly calculate. It's sort of describing like how the pixel information is changing within the sequence. So the idea is like they could collect a sequence of images and they could automatically have optical flow labels come out. And so then the thinking goes like, okay, if our model here could learn to sort of encode this image data together with these other sensor data into a feature vector, and then learn to decode that information back out into optical flow, maybe the optical flow signal would be a sort of a training signal for the model to learn how to summarize that RGB information, which we don't need human annotators to annotate the optical flow. So that might be like one training signal that can be self-supervised. A second one then was, they had like these summary kind of statistics about what was it, like whether or not the like this like measurements of the force and the torque from the sensors will correspond to, what was it, like making contact with, like, let's say the table. So they had like a few of these labels that can be automatically generated. And then what they're trying to do is, so they're just like taking the raw input, encoding it down into a latent space, and then trying to decode that into these like automatically generated types of labels, so that their loss function in this case is like self-supervised. They don't need human annotators for the training of this portion. And so that kind of encapsulates, generally speaking, what self-supervision tries to do. It tries to introduce some automatic like annotation mechanism so that you don't need as much human annotated data. So another example so like this second example, this VIC reg L is like a pure vision example. So they were trying to, like, they define a loss function that can try to sort of like map spatially map feature points from different like crops of an image and use that as training signal for then like downstream classification. So you sort of use this automatically defined like self-supervised training approach to like learn a feature encoder. And then you would use some fewer set of human annotated labels on like a classification model that would be downstream. And so this idea of like self-supervision then has kind of been expanding into the different sub areas within robot perception. So we talked last time about dense object descriptors, which tries to like allow a model to map point-to-point correspondences even across categories of objects. So you could sort of detect in this case, like if maybe you have like an example image and you point out like this pixel on the shoe, what you might want your model to do is, given some new image that was unseen during training, find the corresponding 3D point on that model. And so like a dense to dense object description would let your network do that, which then maybe you could use for like a downstream grasping tool. So once you know where this point is on like a canonical model of a shoe, then maybe you could tell a grasper, like a robot grasper, where it should go to grasp it. So self-supervision has been used to train these dense object descriptors. It's also been used for 60 pose estimation. So this is a paper I think is really, really interesting. They have no 60 pose labels in this data set. And they have 2D annotations for each of the images of these objects. And they're able to still train a model that can predict 60 pose. That is really cool for those of us who work in pose estimation, because labeling 60 pose, like we saw in Progress Labeler, is really, really a pain for humans to do. So the notion that you could train a pose estimator where you don't actually need human annotated 60 pose is really fascinating. So self-supervision, the kind of overarching goal is to reduce the need for human annotated data. And you use some of these automatic sort of labeling strategies to try and get some training signal in place of the human annotated data. So that's self-supervised learning. So from there then, more towards like the manipulation side of things. So grasp pose detection is is the next topic. And so here, so these set of papers give kind of a nice overview of some of the trends. So some early work from Joseph Redman, for example, was like a pure CNN approach to regress like a 2D bounding box in the image about where a gripper could grasp different objects. So Joseph Redman is also like the author of YOLO, which we'll talk about. So that was also an object detection framework where you want to detect the bounding boxes of categories of objects within an image. So this is kind of a similar work, but for robot grasping. An example of a model that does not use so much deep learning, but this gives like a nice contrast to how a lot of like non-deep learning grasp detection works is this one where they use like just known geometric features. They use a bit of machine learning, but these two kind of give, I think, a nice contrast of like a pure CNN approach versus like more like human engineering with like known geometries of objects approach. From there then, so more recently, so DexNet, then Contact GraspNet, and then even more recent that sample efficient grasp learning are a few examples of like pure deep learning approaches that you look at. So the idea with grasp pose detection though is if our robot is going to start to manipulate objects in the scene, a prerequisite is we have to specify the exact pose for where the robot's manipulator should actually go to pick up or to move an object. And so all of these works are going to try to predict that pose for the downstream like planner. So similar to that then, like some additional information which we could potentially use for our grasping or our manipulation is tactile data. So that's data similar to how we have like a sense of touch. There are sensors that you can have on robots that can try to emulate what we humans have in terms of a sense of touch. So these can be sensors like the proprioceptive sensors that can give like the joint encoding of the different joints on a robot manipulator. You can have sensors that give like the force to torque sensors like we saw in that earlier paper. There's also sensors that can give that can read like deformation on a deformable pad, kind of similar to the sort of pads on your fingers. And so that information is actually what's used, I think, in most of the papers that we have here. So the work here are pretty interesting. So one, for example, like try to use is one of those tactile sensors that can read like the deformation on these sort of pads, these pad-like sensors, to try to estimate then the pose of an object that the robot's holding. Kind of a similar one, which I think is pretty neat, is using those tactile sensors to actually map out what the object geometry is for an object in the grasp of a robot manipulator. So these papers here give a nice kind of overview of tactile perception for grasping manipulation. There's a lot, like this is a really cool area. So there's a lot of other papers that we have in the extended section too, if you're interested. From there then, so I think this is the last then broad topic area is what we call these pre-training for robot manipulation, and then also transformer architectures. So really most of these are transformer architectures. So what is a transformer architecture? I think we're going to spend some time within one of the upcoming lectures to talk about this in more detail, but transformers originally were used within recurrent neural networks to try to improve their training on long temporal sequences. And so where transformer architectures were first really introduced was for natural language processing, where if you have a neural network that's trying to process natural language, that's naturally encoded into a sentence structure, sort of this sequential sequence of characters, right, or words or audio signal. And recurrent neural networks struggle with a vanishing gradient problem, not too dissimilar to kind of the rough concepts we were talking about in lecture yesterday, where the deeper essentially that you try to train a recurrent network over time, the gradients inherently are going to get smaller and smaller and smaller. And so there was a paper called "Attention is All You Need" that introduced for natural language processing this idea of like a transformer architecture that could solve that vanishing gradient problem. And recently these transformer architectures have been extended even to vision. So there's vision transformers that try to basically break down an image into a sequence of patches and then treat that sequence of patches as a sequence for a transformer architecture. And you can still do like classification tasks and segmentation tasks actually even better than our pure convolutional networks. Within the robotics community, what transformers have been used for is pairing language and vision together so that we can start to give commands to our robots and have them interpret those commands. So it's kind of a blend of these vision transformers with the natural language transformers. And the results in some of these projects are really amazing. So in particular, So SEICAN and this robot transformer paper they're both from Google, just like within the past 2 or 3 months. And these are not all the authors, because if you look at these papers, they're huge projects. They're like 40, like on the order of like 40 to 50 authors on these papers. But they have some really amazing results where they can, so like in these papers, like in SEICAN, like you can give a robot command to clean up a table, and at that high of a level, and it will actually go and execute like plan out a sequence and take perception along the way and plan out a sequence of actions to solve that. So it's pretty amazing. Now, the amount of engineering that has gone into these 2 papers and the amount of data that they have and resources is also pretty amazing. So I will point out, like, there's a distinction, I would say, between these industry papers and the academic papers that we have listed, just in terms of like the resources. And that's an important thing to think about when you go to like re-implement the paper. Because as much as it's like, I might like to re-implement, SEICAN, like on my desktop GPU upstairs, I could not do it. I would not have the compute resources to do it. So it's something to be mindful of. SORNet is a paper. So SORNet, where's my cursor? So SORNet is a paper actually that our collaborating instructor at University of Minnesota, Karthik Desing, Professor Desing, was one of the co-authors on this paper. So that uses a transformer architecture, as well as Clipport is another paper that I think is very cool. Both came from Dieter Fox's group, so Clipport is using that same idea of like vision and language to try to plan out actions for the robot to take and then execute them as well. So transformers are a hot topic, kind of similar to NERFs. They're picking up a lot of steam. So that's an exciting area. And so with that covers all the broad topic areas. We have a few more listed on the website, and we'll probably, as the semester goes, as I have some time, like I'll try and add some more to just give some more breadth to just the different research areas and sub areas that are within robot perception. I just do want to briefly point out that on the subject of like interpretable models, I think there could be some really cool projects trying to interpret like robot perception models that exist using some of the computer vision interpretation techniques. So like a lot of the distill.pub articles that I'm posting on the reading list, and a few of them are posted on the papers page. I think taking some of those techniques and applying them to like a pose estimation model could be really cool, or a tactile perception model. So it's basically like trying to introspect these deep learning models and try to understand how are they making the decisions that they're making. So one that I linked to for yesterday's lecture reading, like from Chris Oland on distill.pub, which is like equivariance in networks. It's a really cool study of how the individual kernels within a 2D convolutional network sort of learn patterns that are like spatially rotated, for example, so that then you can have detection which is equivariant to rotations. You can like detect any edge at any rotation and then interpret that as meaning like the model's trying to be equivariant for detecting just an edge along any direction. So that's like I think that's a really cool paper. It would be really cool to take some of those ideas and introspect these deep learning models in robots with those ideas. Fairness and ethics is another area that I think is very important that we do think about. So we can bias our robots if we have biased data, and that's something to be aware of. It's something that the machine learning community is certainly very interested in. So we have a few papers that I would suggest you should consider reading, even if it doesn't stand out as like an immediately interesting topic. I think like the ramifications socially of these models that we're putting out into the world is a real thing that we should always be conscious of. And so the papers that we have there and a lot of the other papers in that community do a good job of pointing out some of those concerns. And then these other three, and like I said, I'll try and add more over the semester, but starting to think about some of the niche cases, like the kind of edge cases where a model trained on just a data set from like common household objects might fail. When you start talking about like articulated objects, deformable objects, how you represent deformation and articulation is still an open research question. Having transparency and reflective objects is an open research question. So like mirrors are a huge problem that we have to think about for training our deep learning models. Dynamic scenes brings a whole set of challenges and a lot more. So with that, if there's any questions, like if you want to talk more as a group about any of these broad areas, we could do that now, but then I'll plan to use, the rest of the time I'll kind of go around to the different tables and try and discuss what people have been planning for the projects, or if they want to like go into transformer architectures and try and understand them a little bit better, we can do that. And that's all of today's slide content. So yeah. Any questions I can answer broadly about these topics? So the question was, is it practical to do a transformer paper, like re-implementing a transformer paper? I think it is practical. Don't do those industry papers. Like SACAN and RT1, no. Those ones are not going to be practical to re-implement. But like SORNet, I think, and Clipport, those are reasonable. So for the purpose of like re-implementing papers, I would suggest trying to find papers, first of all, that have code bases available. And then secondly, I would lean towards, this isn't always true, but I would lean towards papers that come from academia. That's not always true. There's a big caveat there, but if you go and look at these like RT1 and SACAN, they will stand out as more like true engineering efforts. I mean, they have a massive amount of resources went into them. So hopefully just from seeing the paper and seeing the lists of authors, that'll you'll sort of pick that up and be like, oh, these are papers that would be interesting to re-implement, but I'm not going to try to re-implement in like a month with like a desktop GPU. Yeah, so yeah, interesting question. So the question was, if we wanted to do a project in tactile perception, would we need a physical sensor to collect data for that, or could we use a simulator? So there are simulators that can simulate some tactile data. I would say that a lot of times these papers will publish their data sets to go along with them. So you can get data sets, not always, but sometimes from the papers that actually publish in these areas. In terms of, so our lab, I don't think we have any tactile sensors. There are other labs here at Michigan that do, but I don't have access to those sensors. So if you're interested in those, like I would say we can, like if you come and talk to us, if you specifically want like new data to work on, we can try and find a way to collect some new tactile perception data. But a good starting point is the open source data that has been published. Okay, cool. So I'll start coming around and trying to get some discussion going and see what people are thinking.